Hello differential equation students. In this video, we'll take a look at how do we solve differential equations using Laplace transforms, especially Laplace transforms that deals with integrals. So to do that, we're going to talk about the Laplace transform, the integral of f of t. In the earlier, we do have formulas for how to do the Laplace transform of derivatives, right? We know how to work with them, we know what to do with them, and so on. So for example, here are the formulas for Laplace, the derivatives of the functions, right? Here are the formula for the derivatives. The question is, what would be the natural question would be, what would be the Laplace of the integrals, right? So let's try to address this in this particular video. So before we do that, I want to quickly talk about something called convolution. So this is something some sort of an integral, but it's a very wonderful integral that can help us solve very many differential equations that has these things, especially Lotka-Volterra and many other differential equations. And these Lotka-Volterra, by the way, the spelling is Lotka-Volterra, and this has a lot of application in many areas, especially in population biology and things like that. So let's take a look at this. What is this convolution, right? This is some sort of an integral, right? So we denote this integral as f star g. This is not a usual multiplication, right? That's not a usual multiplication. This is a special multiplication, if you want to call it, which is what we call the convolution, which is basically integral from 0 to t f of z, which is this f, by the way, g of t minus z. Remember this, right? T of z minus z. This t is the variable of integral. This t is the variable, right, that we're going to plugging it in. The function eventually is going to be a function of t, by the way, right? This is going to be a function of t. This is not a multiplication. This is not a composition, right? And then here the variable of integration is z. This is called the convolution. There are some examples. I'll let you work with those examples, and then for example try to compute this one. If I ask you what would be the convolution between let's just say e to the t and sine t, right? What would that be? That would be, if you go with the formula, that will be 0 to t e to the z g of, in this case g is the sine, so it's going to be sine of t minus z dz, right? And I think book uses sometimes stove, or book uses tau or other notations for variable of integration for z, and that's okay as well, right? The book might use the tau or something like that, or other resources, other literature use different notations. That's not a big deal. Again, there's a variable of integration. It's a dummy variable, so it doesn't matter whatever you want to use. But I'm going to go with the z for the sake of familiarity and the simplicity. All right, I'll let you compute this and see what happens to this, right? That's not the focus in here. I know you're all experts in integration. You can compute them. But what I want to, what is the good news? But before I go to the good news, I want to say one other thing. This is also good news, by the way, and that is the good news number one, or the note 2, is the following, and that is, it is commutative. What do I mean by that? This integral is exactly same as the flipping it up. What do I mean by flipping it up? What do I mean by that is, this integral is same as 0 to t sine z e to the t minus z dc. That's a good news, because then this is sine t convoluted with e to the t. So in general, right, the good news is it is commutative. What do I mean by that? By which I mean, if I just move this up over here, by which I mean this f star, f convoluted with g, is equal to g convoluted with f. That's a good news number one. The good news number two is, the beauty is the Laplace transform of f convoluted g. It's not a multiplication, right? It's not a multiplication that you wonder why we are using this asterisk, right? It's kind of like a multiplication, right? The reason is this Laplace of f convoluted g is same as Laplace of f multiplied by Laplace of g, and here's a regular multiplication, right? And not only that, this is not, we're not going to use this very much, right? What is very, very useful for us is the Laplace inverse, right? The Laplace inverse of, now that you know this, right? So the Laplace inverse of f of s times g of s is going to be f convoluted with g, right? And and that's what we are going to be using in the next set of problems in solving differential equations. Before I go any further, I want you to think about what would be the Laplace. I started with saying we're going to use the integrals. We have not used the integrals. We did not find the Laplace of the integral. We found something else. The question is, what would be the Laplace of the integral of 0 to t f of t f of t, I should say f of t dt, right? I should say 0 to t f of t dt. What would that be, right? What would that be? So here, I'll let you think about it. I'm going to do some couple of examples, then take a couple of minutes, think about what would that be, but I'll address that in a moment. Now let's take a look at some examples of this convolution, right? So what is this convolution? Let me give you some simple example. Suppose if I ask you, what is the Laplace transform of, let's just take a look, e to the t convoluted with cosine t, right? Then this formula says this is same as the Laplace of e to the t, not convolution, a regular multiplication with the Laplace of cosine t, which we all know that, right? That's standard formulas in there. And if I apply those standard formulas, you would agree with me. This is 1 over s minus 1, and this is cosine, so it's going to be s on the top divided by s squared plus 1. So the Laplace transform of this, which would be s over s minus 1 times s squared plus 1. And that would be the Laplace transform of, if you really write it, it's going to be 0 to t e to the z cosine t minus z dz. Right? Let me give you another example. What would be the Laplace of sine t convoluted with cosine t? Right? If you want to use some books might use this notation too, right? Some literature might use that notation too, just to distinguish between the multiplication. That's okay as well. So what would that be? And that would be Laplace of sine t multiplied by Laplace of cosine t, which is, by the way, is 1 over s squared plus 1 times s over s squared plus 1. If you multiply these two, it's going to be s over s squared plus 1 the whole square. And these are very, very useful when we deal with inverses. When we deal with inverses, these are very, very important and very, very useful. All right. Now let me get back to this question, the one that I asked you earlier, right? How do we deal with this? Right? How do we deal with that one? If you really pay close attention, ladies and gentlemen, you would see that in this one, if I take f of z, I'm going to keep the f of z as is, but if I keep my g is equal to 1, what's going to happen to this, right? What's going to happen to this? You would see that f convoluted with 1, which is going to be 0 to t, f of z, and then g is 1, so it's going to be multiplied 1 times dz. That's actually, as a matter of fact, 0 to t, f of z dz. Again, it does not have to be z, it could be anything, right? That's great. Now if I ask you the question that what is the Laplace, what would be the Laplace of the integral of 0 to t? I think it's all, this is all messed up. There should not be f of t, by the way, it should be f of z, dz. That should be f of z dz. Right? Then I can use this one. If I use this one, right, if I use this particular one, then you would see that this is the Laplace of f convoluted with 1, which is Laplace of f times the Laplace of 1, which is, by the way, cap f of s is the symbol, and this one is 1 over s, right? And so therefore what I have is f of s over s. So if I simplify, what I'm trying to say is the following, that the Laplace of the integral of a function, Laplace of the integral of the function is simply f of s over s. I'll tell you an easier way to remember. You know, the integral is the antiderivative, right? Integral is the antiderivative. You all know that. If I ask you what is the Laplace of if I ask you what is the Laplace of the f prime of t, we know that that's going to be s multiplied with the cap f of s and minus, you know, f of 0, right? Here s is being multiplied, correct? Here the integral is the antiderivative, and here naturally f is being divided, right? Kind of the anti-multiplication is the division, right? So, you know, an easier way to remember this. So that's it. Now we know how to do the Laplace of the integral. Let's try to solve a couple of problems in here. Now we know how to do this, right? We can solve a couple of differential equation. But before I do that, I want to quickly do a couple of inverses, and then, you know, to see how these inverses are going to work, and then let's see how do we work with the inverses, and then how can we use them later. So let's take a look at you know, inverses. So if I ask you the following question, what would be the Laplace inverse of 1 over s times s squared plus 1, right? What would that be? That would be, I'm going to rewrite it as Laplace inverse of 1 over s times 1 over s squared plus 1. You know that the Laplace inverse of this one is 1. The Laplace inverse of this one is a sine t. So this is going to be 1 convoluted with sine t, because the Laplace inverse of this is going to be 1. The Laplace inverse of this is going to be sine t. And what do I mean by that? So that's what I have here. So what does this mean, right? This would mean integral 0 to t 1 times sine t minus z dz. That's too much to do. I don't want to do that. But we do know that the this one is, I mean, there's nothing wrong in doing that, but I don't want to keep on do that. But we do know that this is commutative. Remember the good news. This is commutative. So this is same as sine t convoluted with 1, which is equal to 0 to t sine z times 1 dz. And if I integrate that, you would agree that I am going to have cosine z 0 to t, which is going to give me cosine t minus cosine 0, which is cosine t minus, well, actually there's a negative in here, there's supposed to be a negative in the plus, so it should be a plus. So if I rewrite it, this should be 1 minus cosine z. Excuse me, 1 minus cosine z, and that is how we would, you do the Laplace inverse in solving these problems. I'll let you try a few things, right? Here are a couple of tries, right? You try these things. You try the following problems. Find the Laplace inverse of 1 over s squared times s over I'm going to say 1 over s minus 2, and try this. Laplace inverse of 1 over s squared times 1 over s squared. I'm going to say s over s squared plus 9. Try these problems, right? And using this using the Laplace inverse, try these problems and see what you get. Now let's use this to solve what integral equations or integro-differential equations. So what are these integral equations or integro-differential equations, right? What are these? Integral equation is very simple. An equation that involves integration is the integral equation. Integro-differential equation is an equation that deals with integral and the derivatives, right? It's called integro-differential equations. Let me give you a couple of examples, even from your worksheets, right? Let me give you a couple of examples from your worksheets. Here is an it's an integral equation, because this equation involves integral of the function f of t, and that's what you're going to solve. Here is also another integral equation. Here is also another integral equation, and here are integro-differential equations. You see here you have a derivative and you have integration, so that's an integro-differential equation. Integro-differential equation also always comes with an initial condition or initial conditions, depends on the problem, right? So that's the integral and integro-differential equations. Now let's try to solve this problem. I'm going to solve this problem, right? I'm just going to take a variation of this and then solve this problem. Let me quickly do that. Let me take a variation of this problem and then solve this, right? Let's solve this integral equation. So what I'm going to solve is, let me solve f of t plus integral 0 to t. I'm going to say 2 f of t dt is equal to 5, right? How do we do that? The process is the same process. I don't want to repeat the same thing over and over again. We have an integral equation right now. We have an integral equation, right? And here, as a function of f of t, we're going to use the Laplace transform to convert it into an algebraic equation in terms of cap f of s, and then we are going to solve for the cap f of s. Once we do that, we are going to use the Laplace inverse transform, right? Here we are going to use the Laplace transform, and then here we are going to use the Laplace inverse transform, and then you're going to get f of t, the solution, right? Here the solution, and that will be a solution to that integral equation, or integro-differential equations, or I should say, or integro-differential equations. Excuse me. All right, now let's quickly do that. Step number 1, we're going to take the Laplace transform on both sides. When I do that, this is going to be Laplace of f of t. Again, I'm going to skip a step and I'm going to use the linearity property. This is going to plus 2 times the Laplace of 0 to t f of t dt. I should not use the f of t. That's a very bad notation. Sorry again. This is f of z dz. It's nothing wrong, but it's a very bad notation. We cannot have the limit same variable as the variable of integration, and this is going to be Laplace of 5, right? If we do that, what happens? All right. Now let's take a look at how do we solve this. All right. Now this is a Laplace of f of t is simple. Laplace of f of t is simply cap f of s, and plus 2 times this would be f of s over s, the formula which we just learned, is equal to 5 times 1 over s, right? As simple as that. And now if I do the integral, it is going to give me, if I now I'm going to do the, stop it. Now if I simplify this, that is going to give me cap f of s, and this is going to be 1 plus 2 over s, right, is equal to 5 over s. And if I solve for f of s, but before we do that, let me simplify this. This is going to be s plus 2 over s, and here I have a 5 over s, and s and s gets cancelled. So what I have here is, if you simplify this, what I have here is, I have cap f of s equals 5 over s plus 2. And if I do that, this is my second step, right, isolating it for cap f. Step 3 is to do the Laplace inverse. If I apply the Laplace inverse transformation, then I'm going to have Laplace inverse of f of s equals Laplace inverse of 5 over s plus 2, which is left hand side is f of t, the right hand side is 5 times e to the negative 2t, and that's your solution to this integral equations. Now I'm also going to do the integral differential equations, very simple one, not a lengthy one, very simple one, very similar to this one. I'm just going to do one small change in here and let's see how does that change few things. So here's the solution to the integral equation. Now let's take a look at how to solve Integro-Differential equation. I'm going to do the same problem. I'm going to do one small change, or a couple of few changes. Let me just take this 2 off. Let me change this to, for the sake of simplicity, let me change this to 1. I'm going to make the derivative. Since it's a differential equation, I have an initial condition. I'm going to make my life easy and say this is f of 0 is equal to 0. Now what you have here is Integro-Differential equation. So here's your example 2. So here's your example 2. Alright, now let's see how do we solve this Integro-Differential equations. Same method, same step, the same way we did earlier. The step 1 is to apply the Laplace transform and then solve for cap f and then take the Laplace inverse. Alright, now let me quickly do that. Here I have Laplace of f prime of t plus Laplace of 0 to t f of z dz is equal to Laplace of 1. If I do that, then if I use this, if I find the Laplace, this is going to be s times the cap f of s minus f of 0, which I made it to be 0, so that's not a big deal, plus this is going to be cap f of s over s is equal to 1 over s. And this is 0, that's a history. So now if I group the f of s, right, then I'm going to have s as my first term and 1 over s as my second term, right, is equal to 1 over s. And if I simplify this, furthermore, this is going to be s squared plus 1 over s of cap f of s is equal to 1 over s. For the sake of simplicity, let me just move this one over here, or let's just keep it here. Now if I solve for cap f of s, right, that's, so here's my step 2. This is going to be, this s and s gets cancelled. s and s gets cancelled, so I'll be left with 1 over s squared plus 1, and then therefore if I make some space in here, next step is to find the Laplace inverse, right? Laplace inverse, we need to apply the Laplace inverse. I'm going to have a Laplace inverse of, cap f of s as my left hand side equals Laplace inverse of 1 over s squared plus 1. And if we do that, then we are going to have the following. Then this left hand side is going to be f of t, and the right hand side is going to be, since it's a 1, it's a constant, so it's going to be sine t. And if you try to solve this without Laplace, it's almost, it's very, very challenging to solve this problem without the Laplace. And you see, it's a very simple method, very simple process, not too long of a calculation. It made our life much simpler in solving this one. Let's do one more problem involving the convolution, and then we will move on. All right, let's try to solve this problem that involves convolution, right? So we're going to again use the same method that we have been using all along, right? That's the same process that we're going to do right from here, from integro-differential equation that involves convolution, using Laplace, get into an algebraic equation, and then we're going to solve that algebraic equation for f of s, and then once you do that, we do the Laplace inverse to get the solution f of t, right? Let's do that. The very first step is, apply the Laplace. Let's do that. If I apply the Laplace on both sides, then I'm going to have a Laplace of y of t equals Laplace of sine t plus Laplace of 0 to t e to the minus z y of t minus z dz. I want you to stare at this part for a while, so to see how can I rewrite this in terms of the convolution. If you stare at this long enough, right, you will realize that this is actually, this part right here is actually e to the minus z convoluted with y of t. For some of you, it might be easier to see. For some of you, go back and look at the definition of the convolution, right? Definition of the convolution in here, and that will be helpful for you to make you realize that. So once you realize that, then our life is easy. Then what I can do, I can replace this right here. I can replace this right here as simply e to the minus z convoluted with y of t. I should say it should not e to the minus z, it should be e to the t. Right? And the good news is we can use the Laplace properties, the convolution properties. The left hand side is simply going to be cap y of s. I'm going to simply write cap y. The right hand side, the first term is easy, it's a sine t, so it's going to be constant on the top and s squared plus 1 on the bottom, no big deal. The second one is, this is going to be the Laplace of e to the minus t, and then the Laplace of y of t. Laplace of y of t is y of t, that's not a big deal. And Laplace of e to the negative t is 1 over s plus 1, right? And that's it. Now we have an algebraic equation, right? We have this algebraic equation right here, right? In terms of cap f of s. The next step is to solve for the, cap, in this case, y. The next step is to solve for the cap y. So I'm going to group all of them together. When I do that, I'm going to move this one. I am going to move this one on the other side, so it's going to be negative, right? And I move this one, it's going to be negative. So when I do that, what I'm going to have 1 minus 1 over s plus 1 of cap y is equal to 1 over s squared plus 1. And if I simplify this furthermore, what I'm going to have is I'm going to have s plus 1. I am now doing the common denominator of my left hand side. And this 1 and 1 gets cancelled, so I have that times y is equal to 1 over s squared plus 1, right? Now what I'm going to do, let me simplify this furthermore. If I simplify this furthermore, what I'm going to have is the following. I have s over s plus 1 y is equal to 1 over s squared plus 1, right? If I simplify this furthermore, you see that I am going to have y to be s plus 1 as my numerator, and the whole thing is divided by s times s squared plus 1. Here I am going to have to do the partial fraction, but before I do the partial fraction, let me simplify this to make my life easy. This would be, you would agree with me, this would be s over s times s squared plus 1 plus 1 over s times s squared plus 1, and s and s gets cancelled. So what I have is I'm going to have 1 over s squared plus 1 plus 1 over s times s squared plus 1. Now I have to apply partial fraction on that particular one, right? I will apply that. That's a very simple partial fraction, by the way, but I will apply that in a moment. But that's what I have. Let me summarize what I have in here. So what I have here is capital Y to be that one. I'm going to do some reorganizing so that you can see the entire problem, right? Let me quickly do that. All right, now that we're done with our reorganization, now the next step is, this is our step 2. This is our step 2. Now the step 3 is to find the Laplace inverse. So if I do the Laplace inverse, right, then I'm going to have Laplace inverse of cap y, right, is equal to the Laplace inverse of 1 over s squared plus 1, and then plus Laplace inverse of that. But if you really do some partial fraction on this, let me quickly show that. 1 over s times s squared plus 1, if you do the partial fraction, you're going to have 1 over s minus s over s squared plus 1. The idea is, when you multiply this s with this, you're going to have s squared, and then you subtract s squared s squared from s squared minus 1. S squared minus 1 is going to go over here, and then you subtract s squared, you're going to have 1, right? That's the idea behind that. But anyway, if you don't know how to do that, if you don't realize it, use the partial fraction. And so therefore, now I can rewrite this part as the Laplace inverse of 1 over s minus Laplace inverse of s over s squared plus 1. Again, this is coming off of from here, right? That is coming off of from there. So basically this is this, right, which can be written like this, and then this is coming off of that. And when you do that, what's going to happen is that now the life is very, very simple and easy. Now we have a solution beautifully as y of t as my left hand side. The Laplace inverse of 1 over s squared plus 1 is, it's a constant, so it's going to be sine t, constant on the top. 1 over s is simply plus 1, and then minus s over s squared plus 1. S is on the top, so it's going to be cosine t. So therefore the solution is y of t is equal to 1 plus sine t minus cosine t, and without the Laplace, I don't know how else we would solve it. Laplace is, kind of a lifesaver in finding the solution to this particular problem right here. Without the Laplace, it will be very, very hard to get to the solution right here. All right, I will stop it right here. I'll see you in the next video.